In this work, we propose a novel deep neural network for gate perception that is accurate, efficient to implement, and robust to gate both chains and background perturbation. GateNet is implemented as a convolutional neural network followed by a single fully connected layer. The network takes an RGB image as input and produces a 3D tensor as output. The output tensor includes gate predictions for each spatial regions of the input image. For each gate, GateNet predicts a confidence value between 0 and 1, an offset of gate center in x-axis, y-axis, and distance and orientation relative to the drone. For training, we collect a large-scale dataset called AUDR that addresses different scenarios in gate perception in drone racing. Each image in the dataset is annotated with the gate center in pixel coordinate, relative distance, and orientation. There are more than 30,000 samples in the dataset. We evaluate GateNet with AUDR dataset for different cases and compare with the state-of-the-art methods. GateNet requires significantly less memory and achieves a superior inference rate. Overall, GateNet has better performance compared to the baseline. GateNet is implemented on a JSON TX2 on a fully autonomous drone system. Raw images are captured by a high-frequency camera. We choose a fisheye lens for the RGB camera because it provides wide field of view. It helps the drones to see the next gates even when they are very close or far apart. RGB images from the cameras are fitted into GateNet. For state estimations, we use an Intel tracker camera and an IMU to estimate the odometries and altitude of the drone. A gate pose estimator uses GateNet predictions and the current drone state to back project the gate into a global 3D map. A low-frequency global planner uses the map to plan a path through multiple Pacific gates to finish a race, while a high-frequency local planner will plan a safe trajectory through the next gate. The trajectory is tracked by a controller that sends thrust and altitude commands to the lower-level autopilot to drive the drone. To test the robustness of GateNet, we disturb the background environment with a moving human holding a similar gate piece. The prediction is obviously not affected. We also change the locations of a gate in between a lap and find that GateNet predicts the new locations correctly, allow the drones to safely pass the moved gate. Lastly, we change the orientations of the gate, and again, GateNet predicts the new orientations correctly. Through multiple experiments, we conclude that GateNet is robust to background perturbations, gate position and orientation change. It is also efficient to implement on a real system.